Oleg Lavrentovich from Kent State will tell us about electrically driven dynamics of small particles in liquid crystals. This thing doesn't stay on.
Thank you. So let me introduce our research team. It's two graduate students. Oleg Lavrentovich just finished his studies, and Laza Martinez, who just started. Sergei Shayanovsky is a visiting scientist in my group, and we did this work in collaboration with the group of Professor Jack Kelly, who is simulating, computer simulating the hydrodynamic effects in liquid crystals. So we are dealing with the simplest type of nematic. It's not the active nematic, it's not the pleiotropic nematic, it's just the nematic that is known in display applications. So it's the so-called thermotropic material. You hit a certain molecular crystal and it melts. First it melts into the nematic phase in which the molecules are parallel to each other, but they show no long-range positional order. And then at some somewhat higher temperature, you melt it into the true isotropic phase with no positional order and no orientational order. So as I said, the claim to fame for these materials is display applications. Some 80 years ago, Oleg Lavrentovich in the former Soviet Union discovered famous effect, the so-called Frederick's effect, that when you apply electric or magnetic field to the aligning slab of the liquid crystal, the molecules reorient because of the diamagnetic or dielectric anisotropy. And in late 60s, Jim Ferguson at Kent discovered that in a particular geometry of director orientation in the so-called twisted nematic cell, you can achieve a very good optical contrast if you would place the nematic cell driven by electric field between two polarizers. And that gave rise to all the wonderful informational displays that we are using nowadays, sometimes without realizing that most of them are working on the very same principle of the twisted nematic cell or somewhat modified cell. By the way, at that time, it was astonishing that between December 30th, 1969, when he put the scheme in his notebook and the first commercial product that he produced with his startup company, Elixco, in Kent, we had just about 11 months. So today I'll be talking about something that is somewhat different from the majority of talks here, which are concentrated on, let me say, collective behavior or hydrodynamic behavior of swimming of relatively complex particles or their groups in a relatively simple fluid, which is isotropic fluid. In our project, we are starting to look into the motion of relatively simple particles, and I'll be talking exclusively about solid spheres, but they are swimming in a complex medium, a nematic liquid crystal. So that allows us in some cases to direct the motion of the particles, and also it adds new levels of complexity, because in our case, in addition to the velocity field, we also have the director field that shows the orientation of the molecules, and we also have the electric field that can realign the director field. And the subject of interest, as I said, will be a sphere, a solid sphere, and at the surface of any material in contact with the liquid crystal, an isotropy of molecular interactions result in the so-called anchoring direction. And in our case, experimentally, we always achieve a situation when the liquid crystal director wants to be perpendicular to the interface. So if you have a sphere, you have a kind of hedgehog around the sphere. So what would happen if you would throw this sphere into the uniformly aligned nematic liquid crystal? Obviously, the Farfield, which is uniform, has to be somehow matched with the radial distribution around the sphere. And in most cases, the compromise is achieved by this configuration that was described in details by Tom Lubensky and David Weitz at that time at UPenn about 12 years ago. So what you have here is an elastic dipole. You have the radial configuration around the immersed sphere, And then in order for it to be matched with the uniform Farfield, one has to create an additional distorted configuration, in this case a hedgehog point defect, so-called hyperbolic point defect, shown on the left. Topologically, it kind of simply means that you balance the class 1 topological charge of the sphere, the radial configuration, with a -1 topological charge of the hedgehog. And since the surface conditions at the sphere introduces these director distortions, you have a situation when you modify the colloidal interactions in the nematic fast just because of the elastic distortions of the field. For example, you can show that these elastic dipoles will try to attract each other along the line to form chaining, and that was shown experimentally. So in experimental cell, if you just throw these particles, if the original orientation is horizontal, you can easily understand that you might have 50% of the particles that create the hedgehog on the left-hand side, and 50% that would have this hedgehog on the right-hand side. So you would have left and right left and right dipoles. Another thing, if you would take a three-dimensional microscope that shows you director orientation in three-dimensional space, and we developed such a microscope to study phenomena like I am talking about today, you would also see that the particle, this dark disk, is kind of levitating in the bulk. It's not dropping at the bottom, despite the fact that it's somewhat larger than the typical colloidal side. It's about 4 or 5 micrometers in diameter. And so the reason is, again, the nematic nature of the material. What you have here is that the force of gravity that pulls the particle down, because the particle has a density that is about 2 times higher than the density of the liquid crystal, and that one is close to the density of water. So this gravity force is being balanced by the elastic repulsion between this dipole, the distortions around the particle, and the wall. At the wall, the surface anchoring is planar, in-plane alignment, and it doesn't want to see any director distortions nearby, so it creates the force that pushes the particle up. And you can develop a simple model using the image forces, and you would realize that for typical sizes, let's say 5, 10 micrometers of the particles, this elastic force is sufficiently strong to overcome the gravity force, and you can then measure, for example, as the function of the cell thickness, how far away from the middle plane the particle would shift. And you would see that for relatively thin cells, the particle is almost in the middle of the cell, like for this 20 micrometers thick cell. And it just stayed there. It's interesting that if you make your particle bigger, then it would levitate even better, because the elastic force goes as r to the power of 4, and the gravity is obviously proportional to the wall. So what would happen now if you would reorient the liquid crystal as Fredericks did in his experiment? So you just apply electric field. In our case, it's directed from top to bottom and then from bottom to top, because it's an alternating field. We are not dealing with any ionic motion in this case. It's purely the electric anisotropy effect. Of course, you break the symmetry of the director distortions, and it turns out that, as you see from the slide here, the particles which are dipoles start to fill this. The right dipoles move to top surface, and the left dipoles move to bottom surface, simply because of the S-type of distortions in the cell. And then, if you recall a number of previous talks about the nematic hydrodynamics, it was stated that when you have a shear, that shear flow would align the liquid crystal. There is an opposite effect. It's that when you reorient the director, it creates a material flow in the cell. And the symmetry of this flow is such that in the center you have zero flow, but above the center and below you have increase in the velocity as shown here, and then at the two solid boundaries you have a no-slip boundary condition, and the velocity is 0. So, and this simple double symmetry breaks the configuration in the cell, and when you watch what these particles do, those of them that have the hedgehog on the right move into one direction, and those of them who have the hedgehog on the left move into the opposite direction. Those are the very same particles. It just happened that when they were thrown in the matrix, they acquired this left or right satellite. But then when you apply the field and driving the director back and forth, they start to move, and they move strictly according to their polarity. And you can play different. Well, before you start playing games, you would like to understand whether you have the phenomenon understood correctly. And for that, we just used the simplest model, namely the hydrodynamics of the electric crystal that is driven by the electric field. So what you have here is the director reorientation. That is the angle between the director and some axis, let's say the vertical axis that is z-dependent, this angle theta. And then you have the balance of torques. One is the elastic torque that is entering the G sub theta. K1, K2 are the elastic constants. And also the dielectric torque that reorients the electric crystal. And you have also the hydrodynamic contribution to the torque. So the second equation is the linear momentum balance equation. And you also can find in literature the values of all these viscosities, alpha 1, alpha 2, alpha 3, for the given material. And then you start simulating. You throw away, by the way, the particles, because the idea is that since the velocities are not that high and since the sizes of the particles are small, you're dealing with no inertia regime, low Reynolds number regime, and the particles just passively follow the flow. And so then you calculate what would happen if you apply the field. And we are focusing on the z coordinate that is close to the top plate and close to the bottom plate. You see that after you apply the field, the velocity profile requires this non-monotonic force. The reorientation forces the flow, and then it decays. And if you switch the field up, you have a relaxation, and you might notice that the velocity here is much smaller because this is the passive relaxation according to the boundary conditions at the substrates. And the most interesting thing is that if you now take the entire cycle and calculate director dynamics, you would realize that the velocity, the net velocity over the cycle is not zero. And then you match your computer simulations with the experimental results, and you see a very classic non-monotonous dependence of the velocity, net velocity of the particles, on the frequency of pulses that you send with your voltage generator. And it's easy to understand why it became in this way, because low frequencies, you just on the system with the number of pulses that are increasing when you increase the frequency, and at high frequencies, the system simply doesn't have time to react to frequently going pulses, and just decreases the velocity. So you can study jamming in this configuration, because if you decrease the particle, then the particles, if you decrease the thickness of the cell, the particles start to jam, and you can have interesting factor dependencies here. And finally, what we are doing right now is, instead of acting on the background, we are acting on this very distorted region around the sphere. And as you might see, this might be something that you can call the simplest swimmer. It's not three spheres, it's just one sphere, but it swims in the pneumatic electric crystal rather than in isotopic fluid, and it can propel itself. Thank you very much.
Thank you. Other questions?
How is that propelled?
You apply electric field, but you apply it in such a way that you do not disturb the Farfield background. Remember, the sphere creates director distortions around itself to match the otherwise uniform director field far away. So most of my talk was about disturbing this far field, and the sphere just moves along. The last slide was about a configuration when the far field is not disturbed, but this distorted region is being addressed with the electric field. And
so just two probe wires, or?
It's the same. It's electric field, two electrodes, and you apply voltage back and forth, and that's it. It's symmetric with time average equals 0. But because of the broken symmetry of the system, the difference between the head and the tail, which is here, and the hedge hook, you have the net propulsion in the dramatic crystal. It wouldn't happen in the isotopic case.
So you have like a resonance frequency of like 5 hertz or something.
Right.
Is there a way to speed that up for the conditions? Where you move it and does it move
Yeah. Yeah, there are some regimes in which you can speed it up to, let's say, 10 micrometers per second.